Hi everyone. My name is Michael, and I work in a company called Hibernating Rhinos. Rhinos that sleep. Um, we create profilers for RAMs, but our main business is this. This is a NoSQL document database that we created from scratch, and I work on it for quite some time now. On internals, I do low-level stuff, some distributed algorithms. And also, as part of my job, I do support calls and post-mortem analysis. So in this talk, I will share some interesting issues I've seen over the years that our clients do, not only with NoSQL databases, but also with relational databases, and what, in general, what I've seen people do with databases. But before the interesting stuff, I have a question for you. How much queries do you think typically a website would do per page load? Anyone wants to guess? Estimation. How much? 9? 5? Yeah, sometimes, and sometimes more, and sometimes it's a lot more. Now, this is, by the way, this is from several months ago. This is not something old. And yeah, this is an edge case, but I've seen websites do dozens of queries per page load easily, and they're not really large sites. So this is a problem, obviously. One of the reasons why it's a problem, because each query, and people often do not think about it, each query has very large overhead. From infrastructure point of view, but also from computational point of view. Now, in general, this often comes to modeling. In relational databases, modeling is simple. You just do normalize, and there is one true way of doing things, and you end up with what you end up, right? So all you can do is optimize and try to use less queries. In NoSQL databases, usually, it's about how you approach the problem and how do you model data. This is something very important that I often see in people that migrate from using relational databases to non-relational databases, not necessarily our database, is they stay in a mindset of normalizing, of treating the data in the same way they did in relational databases. This is, I think, one of the biggest mistakes you can do, because often you can make it work, but the performance will be abysmal at best. So what about it? In general, data modeling in NoSQL is something for a workshop, at least one full day workshop. So I'll try to make it short, because I have lots of things to say and 60 plus slides to show, and I hope I will finish it all. So the normalization NoSQL is not something bad. It is often expected, and why it's expected, especially in document and graph databases, that the principles of modeling and in terms of support of features and functionality, you cannot do quote-unquote joins easily. So usually you won't be able to treat relationships the same way you do in relational databases. And in general, in NoSQL, bad or incorrect data modeling that does not fit your problem domain means more queries, because you need to make up for it. Now, what should you do? You should analyze your problem domain and plan your queries and your indexes and what so on, but I'm getting ahead of myself. Also, there is another thing about denormalization. It's about point in time. That's what I usually call it. And there is an interesting story that I can tell that highlights this. By the way, this is an actual story that happened in Israel, where I live and work. A young woman, shortly after getting married, went with her husband to get a mortgage. They wanted to buy a house. And the bank said, as you would expect, please bring us your payment slips to see what kind of salary you get, and we'll decide. Okay, they brought the needed papers, and they see that her last name, she had her new, supposedly last name for the last 5 years. What do you think has happened? And she was married a couple of months before this event. What do you think has happened? Normalized data. There was a bug in a payment system that the personal details was normalized, and as soon as she changed her last name, it was retroactively changed all the way since she started working there. So essentially, when you think about the denormalization, you can think about it as kind of snapshot of the situation you had during that specific time. And more often than not, this is welcome, especially for financial information. For example, if you think about invoices, and there are in pretty much all countries, there is a retention policy, how much time you need to keep the invoices. And let's say invoice is on the name of a company named X, right? And let's say that 2 years after the invoice was created, the company is bought and sold and changes name. So you does not make sense to change the company name in the invoice, right? So the normalization, as you can see, is not always a bad thing to do. So couple of things that also couple of things that we can do about it. This is something I've seen often overlooked. Various ORMs and various databases such as ours, shameless plug, I know, have an ability to do something that's usually called future queries, which essentially accumulate several queries and group them in one request. This will, using something like this will allow you to drastically and often very drastically lessen the amount of the queries you do when you send them to the database. Now, let's see something else. Let's assume we have a simple task. We want to fetch stuff that was ordered, let's say, for last week, right? So we use entity framework. We open our Northwind model. I'm pretty sure anyone hasn't seen it. Can you raise a hand? Anyone didn't see the Northwind model? Oh, okay. So it's a demo, Microsoft's demo database to just play around, test Microsoft SQL Server. Essentially, it's a data set of something like online store, right? So we fetch the orders in fairly obvious manner. And then if we take a look at the things, we see something like this. Again, lots of queries just for relatively simple task, right? What happened? If you take a look at the code, we fetched for each order, we iterate for, essentially we are supposed to do a left join. That's what you do. That's what you would do if you query the database directly, right? So essentially what we did, we fetched each order separately and then queried it over and over again. This is something called select n+1 problem. It's actually an anti-pattern. And this is another mistake that I've seen come over and over again. It's not exactly a mistake, it's more an anti-pattern, but it's directly related to the huge amount of queries that we see. Quite often the large amount of queries is something like you fetch all the categories and then fetch all the numbers in each category. You know this, for example, in Amazon website, you have amount of items for each category or something like that. I've seen implementations that do exactly that they do for each loop and query the database in each loop, right? So if you take a look closer at entity framework features, this can be easily fixed. You just tell the entity framework that you want to fetch order details together with an order, right? So if you take a look at the traffic, it will do something like this. So instead of n queries, where n is amount of orders, you will make 2 queries. So essentially, it's best to invest time when you're dealing with databases in general to take a look at the features that aimed at preventing anti-patterns like select n plus 1, and that's not the only anti-pattern. So for SQL servers, it's fairly understandable. You just do a left join and you make sure not to do too much queries. For non-relational databases, it's a bit more complicated, and as I said, it's about the questions you want to ask. So such solutions depend heavily on how do you model data. For example, this is a JSON document, and by document databases, by the way, I don't mean Word and PDFs, I mean JSON files, because that's JSON document, because that's usually how you represent a variation of JSON, or Bison, for example, is how you represent documents. So this is an example of how you would model an order if you knew that you will have to make something like that query that I've shown you earlier. You just embed a collection of order details inside of the document. As I said, denormalization, right? And if you think about it, it makes sense, because joins and splitting the data during normalization, and in general, the whole relational database theory was invented back then when storage was extremely expensive, and developers' time was nothing in relation to hardware costs. So relational model in general was invented to solve problems that software developers had about 50 years ago. So what do you expect? In general, the first thing that we should remember when we look at databases, that database APIs and ORMs, and when you talk about databases and think about database functionality, it's only a facade, and very thin facade that behind it has lots of moving parts. And if you do not take into account some of the moving parts, there may be gotchas. Here is an example of a gotcha that is not in relational database. Let's take a MongoDB. So if we have a order like that, and we want to, we know we need to query by city or by country in a where clause, right? We want to filter by city or by country, right? So that's nice. So what do? We take a look at Mongo, and we see that we can make indexes by this certain fields, right? Makes sense. So we create an index that will cover both of those fields. And then we query it by city. That's how MongoDB query looks like. We query it by city, and we see that that it's okay. Queries by index, and everything is fine. Then we query by country, and then we see something like this. Now this is bad. But before I explain why this is bad, let's take a look at this. In some databases, and I mean NoSQL databases, index terms are essentially prefixes. So if you to make 5 fields, by the way, in a relational database is roughly the same. If you take a look at the indexes, you will see that all the terms that you add the fields to, so we index city and country, this will be one large key that its fields are essentially adjacent to each other. So if we queried by city, it was a prefix, everything was fine, right? And if we query by the last part, we cannot find it because it's the last part. So the MongoDB was forced to search by collection. In other types of databases, and Lucene is a very good example of such storage engine. Lucene is not exactly a database, it's a storage engine. By the way, can you raise a hand who heard about Lucene or Lucene.net? Oh, okay. Nice. More people than I thought, because Lucene is relatively unknown in .NET space. Lucene is originated from Java, actually. In .NET, there is a port that's called, as you would expect, Lucene.NET, is a very good and very efficient querying engine, indexing engine. And if you have heard about Elasticsearch and Solr, they all use Lucene behind the scenes. RavenDB also uses it, but RavenDB is a database. So there is another type of index that stores the fields separately, and in this way, for example, in Lucene-based query, if you make an index on those two fields, it won't matter if you query one or the another on both, because it just fetches first one, then two, then whatever fields, and intersects or does any needed set-based operations on them. So in general, collection table scan, it's a linear operation, right? So if you have huge amount of data, it will cost you, and it will cost you a lot of time in production, because that's where you have lots of data. Joel Spolsky, one of the founders of Stack Overflow, summarized it pretty well, because abstractions, and database is just an abstraction for a bunch of algorithms for indexing and storing and querying. They are all leaky, and some abstraction leaks can cause performance problems, and often that's the root cause of when software developers do not take into account abstraction leaks. That's when performance problems start with databases in general. But implementation details, such as how indexes work, is not the only thing I will talk about. So another question. Take a look at those queries, and anyone wants to say if they are different or no? Anyone? Under the hood, I mean. I know the syntax is different. Anyone wants to try and guess? Very different databases. Okay, so the answer is no, they are not really different, because they all go to index ideally. Unless, of course, it's a table scan, but it's an edge case, which should not happen in any case. So in general, indexes work like this. So if you have some data to index, so you just essentially you write for each search term, you write a pointer where it happened, where it occurs, essentially. Very simple idea. Sometimes it's called reverse index. I'm not sure why, but anyway. And indexes are usually implemented as a tree, typically, because sometimes it's other data structures such as tree, and looking up the index is logarithmic complexity. By the way, tree is key length complexity, so if you need something more high performance, is a nice thing to use. And if we take it into account, a relatively simple query like this, and this is a RavenDB query for those who, and you most likely don't recognize the syntax is RavenDB query. Yeah, the complexity, even for such a trivial query, and in any database this will be a trivial query, is not so trivial, right? So we search for one field and then search for another, then we need to intersect them, right? So essentially it's a linear operation, intersection. So it's about the size of the query. And for relational databases, this is even more interesting, because in addition to where clauses, you add a cost of joins, which I mentioned already. They were costly, but they are very, very costly, especially for large databases. And in production, you only have large databases. If you don't, then you don't care about performance. It will be fast anyway. Now, and usually, queries in production look like this. Can you think about the complexity of something like this, and I'm not talking about where clauses, which only add to complexity. So essentially, we'll have a complexity usually too much. So what can we do about it? Usually, and the best thing to do is proper indexing. In relational databases is more because they are more prevalent, so it's more understandable what we should do. We should properly set up indexes, we should optimize queries, we should not do any unnecessary joins. And in NoSQL, except for proper modeling, which we spoke about, indexing planning is extremely important, because if you don't plan indexes properly, you can end up, for example, with collection scans where databases where indexes are essentially searched by prefix, or you can have inefficient indexes for databases that run indexes in the background, for example, CouchDB, if I'm not mistaken, then they run indexes asynchronously in separate threads. So I've seen data, and we also do that in RabbitDB. So for example, I've seen indexes, I've seen databases with 300 indexes that run in the background. And considering that thread pools are finite, what's the performance do you think of indexing was? Not very good. So we can conclude that complexity is also something that abstracted by databases. And complexity is, you should at least invest some thought about complexity of queries and what you do with databases, because more often than not, just reducing 10 joins to 3 join can improve order of magnitude. I remember on my first job, I had a huge SQL query with about 30 something joins, which was running in about 4 minutes. And I reduced it to 3 joins, and it was running in 300 milliseconds. So that's quite a change. Yeah, after some index optimizations also, but you understand what I mean. Now, let's take a look at another interesting thing. This is an actual support call that I took. A client had multiple tenants or databases on one server, right? I had no issue with hardware, so no limits on memory and stuff like that. And it took for a very long time to load the process, and the client thought it was hanging up. So a question is, can you think what would be the root cause of something like this? Anyone wants to try? No one? Well, the answer is very simple. When you have lots of databases and you start up the server, they all start reading from the hard drive because they need to do some memory mapping, some fetching from database, and memory mapping, which is usually what databases use, starts fetching pages to memory, and obviously you saturate hard drive. And the client had, it's a bit more than 200 databases on the same storage, which usually works fine because they were accessed constantly, but for a very short periods of time. But during load up, all of them in the same time started loading. So you can imagine how storage was straining. Another thing that more often than not, people, when they look at the databases, they do not take into account environment. Environmental constraints such as storage, such as network, such as even memory or CPUs, threads, whatever, is finite, and databases are not magic black boxes, and they will struggle. So here's another riddle. Why do you think this would happen? Query that has not much results, query results, right? and it takes very long time to complete. Let's say 5 seconds. I don't remember the numbers exactly, but 5 and 100 looks like a very good number. So anyone wants to try and guess? The answer is very simple, actually. Yes?
Well, I had a guess.
Ah.
Content stored off page.
The what?
Content stored off page.
Good guess, but it's even simpler than that. Anyone else?
You need to scan the whole table in order to find precisely the 100 rows that you're interested in?
No, it was the equivalent of a select top 100. No scanning whatsoever was involved in this. Anyone else? What? Yep. It was a document database, and each document was tens of megabytes of size. And to be more exact, network bandwidth. But that's the right idea. Network bandwidth. So as you can imagine, 100 documents, each between 5 and 10 megabytes of JSON would cost something like this, because the time that was spent on the server actually fetching the query was in the milliseconds, in the dozens, sometimes in the hundreds milliseconds. Now, regarding large document sizes, there is one more thing that usually, when you take a look at NoSQL database, which is a document or graphs, because graphs are usually document databases with relationships that are first-class citizen, but under the hood, usually graph databases are document databases, is how do they do serialization. It may sound trivial, but serialization actually is a very big problem to tackle. Think about like this. You have a document which is of unknown form or shape, right? JSON with unknown form or shape. You need to go over all of its fields recursively, right? You need to do lots of allocations. You need to do lots of recursion, because sometimes the recursion is very deep, right? So I have seen, and in our database, for example, before we changed how we do things, I've seen just the serialization itself take about between 30 and 40% of application time, right? This is a lot. And I'm not talking about garbage collection pauses that are caused by excessive allocations. And we're using JSON.NET, which is very well known and very performant library, but it makes lots of allocations. I mean, lots of them. So one of the solutions that usually database vendors take, they use some sort of pointer arithmetics to get to the point. So for example, we implemented our own JSON formatter that uses that stores JSON with special table, kind of like file allocation table, but stores the offsets of each property, each field inside the JSON. And this way we can access the fields without allocating memory. Another database that are doing something similar from what I've seen is MongoDB, for example. So size does matter also for document sizes, not only for network, but also for how databases do things. And serialization, from what I've seen, is something that not many people think about it. And quite often it's critical for any application. So this is something that I've seen do a lot of good. When you deal with databases, with any database, what I usually do, I take a look at its traffic at certain times during stress testing, during load testing, if possible also during production, because there is no way around it. Database is a application that has a client and a server, right? And again, usage patterns of databases are vary, and usually I mistrust any benchmark. For example, I usually mistrust any benchmarking that compare between databases, because some databases perform well in certain use case, in another use case they're crap, and vice versa. So Don't believe benchmarks, don't believe even your eyes. Use tools to prove that you are doing good things, that you have no any inefficiency, that your queries are doing fine. Because, for example, databases that use HTTP, again, shameless plug, but I work on a database, so I'm biased. RavenDB uses REST API, so you can debug latencies and what the client side sends during Fiddler. But other databases have profilers, or other databases have tools to inspect both the queries and latencies and performance of the network-based component. So this is something that I cannot stress enough. I realize it may sound trivial, but I've seen often people just don't do this. And usually, I've even seen a couple of times people do not set up even monitoring to see if there have problems or inefficiencies in the network, which I cannot understand why, but anyway. Another thing that I have mentioned it before, but resources. This is something that we need to mention explicitly, and I will explain as by an example how does it work. So, for example, we have very nice feature which is I mean RavenDB. So you can get real-time notifications to data that you subscribe on. So if some data changes, the subscriber client will get notification that something happened, right? So this sounds nice, and you can implement lots of nice things with something like this. And we're not the only database that has something like this, for example. Again, MongoDB has something similar. And such feature, unfortunately, gets overlooked a lot. And I'm sure you can even now see how it can help you with implementing stuff. But this is a real case that we have seen. It's the real support call. A production website was opening once per page load, a subscription. So, what do you think happened? What's the consequence of using something like this? In theory, that's nice, right? You have a mechanism that will notify you in real time that something happens, and you can update your UI and and you can do notifications. Something has changed, right? What do you think? Can you try to guess what would happen if something opens once per page load? One of the things, socket exhaustion. That's actually what happened with that client. But that's not the only thing. Depending on load, some more things that can happen. Yeah, it was socket exhaustion because it opens TCP socket from the client to the server, opens persistent TCP socket, which is constantly kept alive, right? And on the server side, it opens a special thread when the subscription is activated, because it's not active all the time. And that thread listens to the changes. Sounds simple, right? But thread pool threads are also something that is finite. And thread pool threads are used, depending on a database, can be used, for example, for accepting requests. So a database with exhausted thread pool can just refuse to request to accept queries, right? And it can happen just because under some load spike, and then under very bad scenario, it can even trigger some other failures and stuff, start timeouting, and it will be very nice call in 3 a.m. Now, in general, special care should be taken to look at thread pool connections or sockets or whatever communication protocol your database had with the client, and bottlenecks, environmental bottlenecks as well. We have mentioned both storage and network bottlenecks. Those usually pop up with support calls and usually pop up when you have inefficiencies in performance. So things, for example, here's a nice example of a storage bottleneck that wasn't apparent, right? We had a client that had a cluster of databases, and the cluster of databases was using Sun SSD drives very fast. It was nice, right? And we implemented cluster using consensus protocol, and this means that uh, and this means that there is a need for some storage capacity when writing, because it stores a state machine, because consensus protocol is a protocol to is a way to propagate state over the cluster, and so all the cluster agrees on certain state, right? So, and this state is persisted, and the cluster was failing at random times, right? And the interesting thing is that usually everything was very fast, right? And during peak times, the cluster sometimes failed during peak traffic. What happened was the Sun drive, all the cluster was sitting on shared SSDs. So when one of the nodes was overloaded, all the other nodes had much less storage capacity to work with. And disk latency fell momentarily, and that caused the race condition to make stuff fail. Now, if I didn't know what happens under the hood, if I didn't know, for example, how the clustering protocol worked, and if I didn't know how the underlying things worked, I'm not so sure if I could have found a solution to, and at least a root cause to this issue. So it's very important to take a look at those resources, to take a look at how they're used by your database, whatever database you use, and just invest some time into picking under the hood of databases. Now, there is another finite resource. It's not really a resource, right? But it's finite already. Concurrency. Now, about concurrency, there is I sometimes see people who just not so sure what it means. So I will at least explain a little bit before. Optimistic concurrency is very simple. You assume that you won't have too much contention on your data, so you have very small log duration only, and if you even have logs, or you do it with kind of timestamp, raw version, or whatever buzzword / term your database uses. And essentially, it comes down to update this record if nobody has updated it since I've taken it to update, right? So a update request comes, takes the query, takes the record, does whatever it needs to do with it, transaction, for example, inside then tries to write it down and sees if nobody has updated it in the meantime, right? So that's in theory very nice. But what if we have several transactions, and one transaction very short, and we have lots of other transactions which edit the same data or try to edit, and they're longer? What do you think will happen? They will just get rolled back, right? And now multiply it by 1,000. Let's say you have 1,000 requests per second. It's a reasonable load for a website. And you will see why optimistic concurrency is optimized only when you have very small contention to the data, right? If you have lots of contention, then you should go to pessimistic concurrency, which is essentially what often happens in relational databases. You have a transaction that changes some row, so it locks the row. You have sometimes the lock is escalates on table, for example. So it's more geared towards lots of contention, and rolling back and retrying transactions is much more expensive than just waiting for it inside the database. Now, the interesting part that each such query is a thread. Usually, it's taken from thread pool. Now, what will happen if you have exhausted your thread pool, for example, by using some other feature that exhausts thread pool? You get very interesting things, so very interesting balance, because thread pool is, as I mentioned, used by several multiple features of single database. So essentially, I like to chart stuff. So this is something that can summarize pessimistic and optimistic concurrency. It's a trade-off, and there is no correct way of going about concurrency or thinking about it. It all depends on your use cases and on stuff that you do, on how do you need to query database, how do you do updates. So this is in general, you shouldn't keep transaction open for too long, because very long transaction, they will either keep other will lock data and keep others from updating it, or they will cause others to they increase the chance that they will get rolled back because of the whatever other short transaction updated the data. So this is it, and I'd love to answer some questions. Yeah, there is a link to open to our source code. If you're curious, you're invited to take a look to RavenDB source code. Anyone? Questions? So I guess this is it. Thank you.